So, now we will look at ARMA model, which is more general one. We will see that how we can compute the coefficients of the ARMA model, if really it is the case that AR model cannot do justice to that signal. So, for that let us look back at the pole 0 model. The general model equation is given here, consists of AKs and BLs, and the first value here, that the for the B0 the value is 1, and corresponding to that, if we look at the spectral domain, we get the spectrum, or rather the estimate of the spectrum S hat y. It can be given as the square of the that transfer function h omega, because our input x n, we have told that x n is either white or it is an impulse response or impulse. Okay. So, as it is constant, it can be represented, the spectrum can be presented only with Hz, and that filter Hz or h omega we can represent in terms of the polynomials A and B in the z domain, and the corresponding actually the spectrum SB and SA, their ratio can determine them. Okay. So, we have given here below that the expression of SA and SB. So, that is the starting point in short. So, from here the total spectral matching error, if we are looking at the error that what we are trying to minimize, we can again give it, the error is sum of the that error in the that time domain as well as that is same as the error in the spectral domain, and the spectral domain error E omega, or rather E omega mod square, it can be represented in terms of the spectrum of the signal S y and h omega, and h omega can be represented in terms of S A and S B. So, using this fact, we can obtain actually that pole 0 model or the coefficients required for that by minimizing the error, the total square error eta. Okay. So, before actually going into that, let us look at some actually small formulas that which would be useful for to do that work. That if we take the partial derivative of the spectrum of the filter Az, that is S A omega at mod z equal to 1, we get it in terms of the error coefficients, that autoregression coefficient A k and some cosine term. Here we actually make use of the fact that when we are talking about z, z is at when mod z equal to 1, okay, then it is represented by e to the power j omega, okay, or rather we take z to the power minus 1. So, minus j omega will come. So, e to the power j omega, this exponential can be represented in terms of cosine omega plus j sin omega. Okay. From there the cosine term is coming into play here. Okay. And for SB also, if we take the partial derivative, we get the summation of the terms with BL and some cosine terms along with it. Okay. We can derive that, we need some time just to do that. And then we take another expression which will help us to write the things in a more compact way. We defined something called phi y alpha beta. So, it is very similar to phi y I. The only thing what we have done, we have used alpha and beta to take the power here, that we have taken in the denominator for SB the power alpha, and for the numerator the term SA has the power beta. Okay. So, that is the special thing what we have done. And phi y 0 0 I is nothing but the inverse Fourier transform of SY, or simply we can write that as phi y. That means, it is a more generalized form. When we take alpha and beta both are 0, we get actually the same old autocorrelation function, okay, of y. Now, why we have taken these, it will be more clear as we proceed. Now, the partial derivative of the error term with AI, that is delta eta with respect to AI, it will give us that the terms SY and SB, they are not actually having any term with AI. So, the partial derivative will be applied only with SA, and we have taken it in that way. And here we make use of that, the previous result, we replace it with the summation of that AK coefficient, the previous result, and using that we can write it in a more compact form. We make use of that, we get the results are coming in terms of some variable phi y 1 comma 0. Okay. So, phi y 1 comma 0 means we have here SB is there, that we got one term of SB, but SA is not there in the numerator. Okay. So, we are getting the equations in that way. Next, in the same manner, we can take the derivative of eta with respect to Bi, and we get the equations in terms of phi y 2 comma 1. Okay. So, we can give a compact representation, we get two sets of equations. Now, if we look more carefully, we observe something, the terms that phi y 1 comma 0, they are not function of AK. So, we get a set of linear equations by equating that partial derivative to 0. So, by that way we can compute the coefficients AK by those p equations, because p equations and p unknowns are there. Now, if we look at the next set of equations, we get unfortunately phi y 2 comma 1, it is a function of again b I. So, it is not a set of linear equation. By equating that delta eta partial derivative of that with respect to b I, equating that to 0, the equations what we get, they are not linear equations in terms of b I, but it becomes set of nonlinear equations. So, what we need to do to solve the AR model or to estimate the AR model parameters, we require to solve p linear equations and q nonlinear equations. So, let us see first how that can be performed. First, we take an iterative technique, because we have to deal with a set of nonlinear equation. So, we have taken the Newton-Raphson's technique, and using that we can compute the values of vector A and vector B, and combining these two together, rather concatenating them, we get a new vector C, that is the vector of actually the model coefficients, and we need to find that using this iterative process. So, we have some update rule. At every iteration we update the value of C, the vector C, with respect to that the previous update value Cm, we get Cm1, and we make use of the Jacobian of eta, rather we are using of the Hessian matrix here. J is the Hessian matrix, that means we are taking the double derivative of the error eta with respect to C, and we compute that at a point C equal to Cm. Okay. So, once we compute that, we can update that value, and this way we can actually compute, and for that part we can actually partition also the two parts to make it simple, that we can write it in this way, that as C is concatenation of A and B, or rather A transposed and B transposed, we can write the update equation in this form, where we have to compute the inverse also here. So, here we can, using that we can get a number of equations using the first and the second order derivatives, and that we can solve these equations. Using these equations we can compute the value of AKs and BLs. However, as we are using some set of nonlinear equation, the results are very much dependent on the initial conditions. If we have good initial conditions, we will get the optimal result, otherwise we may get actually something much inferior than that. So, we look for some alternative. and for that we take one technique proposed by one scientist named Shanks. So, it is known as Shanks method. Okay. So, let us look at that what is the Shanks proposal. Let us go back to that ARMA model. In the ARMA model, that we have taken Hz in terms of the ratio of the two polynomial of Bz and Az, or in the time domain we can have taken that as a linear prediction equation using that few previous values of the output and present and the few previous inputs. So, here what we do, that we compare yz, or rather what we are doing, we are decoupling the two parts that in the ARMA process, one part is the MA part and one part is the AR part. So, we are decoupling the thing in a way, we are for that purpose we are choosing a variable V, which is helping to an intermediate variable, which is helping to separate the or break that this general equation into two parts. One part is the only MA part, another part is only the AR part. So, if we separate these two parts, we can tell that Vn is the signal what we get by the AR model, and using that Vn in that MA equation we can get the output Yn. Okay. So, we are actually dividing the two parts using this new variable Vn. Okay. That is the trick actually is done. We could decouple the two things. Next thing that Shanks has assumed, that let us take that this signal is nothing but the impulse response of that ARMA model, that Yn, it is nothing but the impulse response of the ARMA model what we are trying to estimate. So, in that case, if the input is delta, then the output y has to be Hn, the impulse response of the filter. So, the equation of the ARMA model we can write it in this way, that Hn in place of Yn, we can write it that for first few values for n equal to say 0 to q, this equation will hold, and when n becomes more than q, this part none of them will be present, all of them the value would be 0. So, we can drop this part and it becomes a simple equation like this. Now, what is the benefit we get out of this process or this assumption is that in this way we could actually separate the two sets of coefficients. Here we see in this case that we do not have any b's, this set of equation that is having only the AK term. So, that is the major gain we have done. So, now if we multiply both the side by Hn minus 1 in the second equation, we get actually it in terms of phi h. It is an equation using phi h and the air coefficients AKs. Thus, what we get that using these equations we have actually the n is much larger than capital N is much larger than P and Q. So, in that case we have a number of actually such equations, and these equations they are independent of actually the BL. So, we can first compute the AKs using the value phi h, and that is what is actually done first. So, because there would be some error, approximation error. So, it has been written in this way that we would have some error En, that is the prediction error of the impulses here, and we need to minimize these again eta, that is gives the sum of error square from q plus 1 onward. Okay. So, we are taking the sum of error square because so many equations are there, equations should be here. In this case precisely we have actually p unknowns and we have that n minus q equations which is much actually larger than p. So, more unknowns are there, it is over determined system. So, there we need to take care of the error in that error this over determined system, and the error is defined in this way. We try to minimize that to find out the best possible solution. Now, using that equation, first the error part that air coefficients are computed, and then we get the estimated values of AK, which is represented by AK tilde, and we compute the corresponding the polynomial Az or the estimate of that Az tilde. Now, as we have the Az tilde, we can look for the total square error for the MA part now. We can concentrate in that, and if we try to find that again, we can represent that as the error in the MA part, where we would need the value of V tilde n minus L. Okay. And if we know that, because the Hn is known, we can compute the BLs again in the same way. Now, V tilde n is nothing but the impulse of the air filter, and air filter already we have an estimate. So, using that we can compute actually the value of V tilde n using the polynomial A tilde z. We can compute that, and by minimizing this we can the eta, we can get, this is a set of linear equations that with the help of that again we can compute the value of BL. So, Shanks method again we are getting a set of linear equations. However, in this case it's just we have the q unknowns and actually q that equations. Okay. So, we can actually solve them and we can find out the MA parameters. So, in that way we can get both the values of the AR parameters and the MA parameters using linear equations. Thank you.